Hello. Let's get energized like the bunny. Alright, we're going to talk about phase changes. I remember phase, that's like gas, liquid, and solid. And I guess change would be going from one to the other. Okay, so let's read this. When a chemical changes phase, it has to gain or lose energy. Solids have the lowest energy, then liquids, and gases have the highest energy. So as energy goes up, we go solid, liquid, gas. If a chemical melts, going from solid to liquid, it will have to gain more energy. Makes sense. Solid to liquid gains energy. Therefore, melting is endothermic. So endo means in. Heat is absorbed. Similar logic can be applied to evaporation going from liquid to gas. So liquid, gas, energy is going up. So that's also endothermic. A less well-known phase change called sublimation is also endothermic. Sublimation is when a chemical goes directly from solid to gas. Interesting. So solid whoop, to gas skips liquid all together. Energy is definitely going to go up. Most common example of sublimation is dry ice. Dry ice is actually solid CO2. You can buy this in the store if you're over 18, by the way. So maybe get your mom to buy some. I know the, what is it, Smart and Final at Century and Crenshaw. I know they have dry ice. I think they do anyway. When exposed to room temperature, it will change directly to a gas, absorbing energy in the process. What's this thing? Enthalpy of a system. Remember, enthalpy, for our purposes, is the same as energy. Technically, it's a little more complicated, but we're not going to worry about that. So solid to gas, sublimation. So let's do all the endothermic ones in blue. So this is. That's not blue. What? So this one right here, that's blue. Make it bigger. Blue. Let's see, this one. Oh, so melting is also called fusion. Interesting. And then vaporization, which is boiling, right? Same thing. So those are all endothermic, and they're all going up. Notice that? Yeah, they are. They are all going up in energy. Let's read on. Exothermic processes. You know, I'll bet you right now that's the opposite, like when they go down. So deposition would be gas to solid. Condensation would be gas to liquid, and then freezing would be liquid to solid. And I bet you those are all going to be exothermic. Watch, watch. Exothermic phase changes are ones where the chemical loses energy and must release the energy, right? So if gas has the most energy, then liquid, then solid, anything that goes down is going to be exothermic. These phase changes are the opposite of the ones already discussed. Freezing is exothermic, because when a substance changes from a liquid to a solid, it loses energy. Likewise, condensation is exothermic, when a chemical goes from a gas to a liquid. The third exothermic phase change is called deposition. It is when a gas changes into a solid. There's no example of deposition here, but I want to know an example. So, example of deposition. Desublimation. Oh, so basically it sounds like snow is an example of deposition from this picture. Well, interesting. So it goes directly from vapor to solid without being a liquid. I guess it would be hail if it became a liquid first. Alright, that was fun. The point at which chemicals change phases have special but very common sense names. When a substance starts to boil, it's at its boiling point. Substance will not boil below that point. If heat's taken away from a gas, it will condense at the boiling point as well. So it's really a condensation point and a boiling point. So, and condensation. The point at which a substance melts and freezes is called the melting point. Or freezing point, I guess. Freezing. Either one. Alright, the heat required to change phases is called a latent heat because it does not raise the temperature. Latent comes from the Latin, which means lazy, so it's a lazy heat because the temperature doesn't change. But it's actually doing a lot. For melting, it's called the heat of fusion. I guess that's why melting is sometimes called fusion, not to be confused with the nuclear process. Once the solid is fully melted, added heat will again increase the temperature until the next phase change. This occurs for water at 100 degrees Celsius, or 373 Kelvin. At this point, a latent heat of vaporization is required to turn the liquid into a gas. The latent heat required to vaporize a chemical is much larger than the latent heat to melt a chemical. So that means vaporization is harder, or greater than, or more difficult than fusion, or melting, same thing. These latent heats are often expressed mathematically in terms of a change in enthalpy. So remember, delta H is enthalpy, and we're using it interchangeably with energy. A subscript of F is used for fusion, which is melting, delta HF, and a subscript of V is used for vaporization, delta HV. To find the heat required to change phases, the mass and latent heat simply are multiplied together. Q equals delta H times M. Latent heat can be used to calculate the heat required to accomplish phase change, but is useless when a sample is all one phase. Unless it is currently changing phase, right? Okay. Now, was there a math part to this? I think there was, but it's not on the next slide. Oh, there it is. I wonder if I can get this in here quick enough. Now I'm just making weird noises. You guys are like, oh my gosh, he's dying. I'm not. I'm just, watch, see, I've got to copy and paste it. Here we go. Copy. Now we go back to here. Now we paste it. And now we annotate it. Yeah. Alright, so what's this say? Water's heat of vaporization is 2,260 joules per gram. This is delta HV. If sample of water required 20.3 kilojoules, this is Q. To vaporize, what was the mass of water? So we're looking for M. So Q equals 23.3 kilojoules. That's 1,000 joules. This is in joules. We got to get the units to match. Delta H, M, Q equals M, delta H. We're looking for M. Plug it in. Looks like they divided both sides by 2,060 joules per gram. 2,260 joules per gram. Gram ends up on top because you multiply the reciprocal. You get 8.98 grams. Algebra. Nice. See you in class.